Welcome back to Physics 192. I'm Gerard Blanchard. Starting this time, we're going to get into our third major topic of the course, and that is electrical circuits. Some of the quantities we're going to talk about in electrical circuits you're already familiar with. Two of these are electrical potential, or voltage, and electrical current. Electrical potential, or voltage, is represented by a capital letter V. It's related to the electrical potential energy. It's measured in units of volts, which is a capital V. The point in the circuit where the electric potential is equal to 0 is referred to as the ground, and it's represented by this symbol. Now, the logic behind that symbol and the term ground is that some electrical circuits are literally grounded, meaning that a wire is run from the electrical circuit to the earth. The other electrical quantity that we've already touched upon is the electrical current, which is represented by a capital letter I, and electrical current represents the flow of electrical charge. The direction of electrical current is the direction of the motion of positive electrical charges. If the mobile charges are negative, then by convention, the current is in the direction opposite the charge's motion, the negative charge's motion. So conventional current is the flow of positive charges. And current is measured in units of amperes. We're going to build up electrical circuits, at least initially, out of three components: batteries, resistors, and wires or conductors. A battery is represented by this symbol, where the longer of the two parallel lines represents the positive side of the battery. The important thing for us to know is that the change in electrical potential across a battery is equal to the electromotive force of the battery. The electromotive force is measured in volts, and it's related to the chemical reactions that take place inside of the battery. Inside of a battery, chemical energy is converted to electrical potential energy, and the electromotive force is the energy per charge. For example, a zinc-carbon battery comprises three chemical reactions, one of them within the electrolyte of the battery, one of them at the anode or positive side of the battery, and the other at the cathode or negative side of the battery. In the electrolyte, we have this reaction where two chemicals are mixed and result in one positive ion and one negative ion. The positive ion reacts with the anode, and in effect taking two electrons from the anode, or leaving the anode positively charged. At the cathode, the reaction results in giving the cathode two electrons. The net result of this is to create an electric potential difference of 1.5 volts between the anode and the cathode, where the anode is at the higher voltage. If you've taken general chemistry, then you would have discussed this. 1.5 volts is the overall cell potential of these three reactions, which is determined from the reduction potential of the reactions and the oxidation potential of the reactions. The net effect of these chemical reactions is to pump electrons from the anode to the cathode. The second element out of which we're going to build electrical circuits is the resistor. And a resistor is symbolized by this symbol, a zigzag line. The important equation for us is that the change in electrical potential across a resistor is equal to the electrical current through the resistor times the resistance, capital R, of the resistor. And current flows from the high voltage end of the resistor to the low voltage end. Resistance is measured in units of ohms, which is symbolized by a capital Greek omega. And 1 ohm is equal to 1 volt divided by 1 ampere. That's what you need in order to make the units work out. In the equation, the change in voltage across the resistor is equal to the current through the resistor times the resistance. Let's talk about the factors that affect the resistance of a resistor. Empirically, the resistance of a resistor is determined by 3 things: the length of the resistor, the area through which the current flows through the resistor, or the otherwise known as the cross-sectional area of the resistor, and finally, the intrinsic resistivity of the material. Resistivity is represented by a lowercase Greek rho. We put all this together in the equation. Resistance is equal to resistivity times the length of the resistor divided by the area. So the resistance goes up as the resistivity increases, as the intrinsic resistance of the resistor increases. The resistance of a resistor also goes up if it is longer. So the longer the resistor, the greater distance through which the current has to flow through the resistor. That increases the resistance. Now, if we were to make the resistance fatter so that more current could flow side by side, then that would decrease the resistance of the resistor. So the net effect is that the resistance is equal to the resistivity times the length of the resistor divided by the area. Also empirically, the resistivity increases with temperature. This is represented by the equation resistivity is equal to resistivity sub 0 times 1 plus alpha times the temperature of the resistor minus 20 degrees Celsius. So you can see that the resistivity sub 0 is the resistivity of the resistor at 20 degrees Celsius. If we were to put T is equal to 20 degrees Celsius, then that term, the alpha term, would be equal to 0, and the resistivity would be equal to resistivity sub 0. As T increases, the resistivity increases, and as T decreases, the resistivity decreases. Alpha, which has units of 1 over degrees Celsius, is called the temperature coefficient of resistivity, and you would find that in a table of temperature coefficient of resistivity, together with resistivity sub 0. So we have batteries, resistors, and finally we have wires to connect our batteries and resistors. We call these conductors, and they're simply represented by a line. And strictly speaking, while conductors have some resistance, their resistance is so low as to be negligible. So we say that the change in potential across a conductor, or the change in voltage across a conductor, is equal to 0. So it's so small as that we will not worry about it. So these 3 elements are the elements we'll use to make up electrical circuits. Now let's talk about the equations, our fundamental equations for electrical circuits. There are 2 of them, known as Kirchhoff's laws. Kirchhoff's first law, we'll call Kirchhoff's voltage law, is that the total change in voltage around any loop is equal to 0, or delta V total is equal to 0 around any loop of the circuit. And that makes sense. If you start off at a certain voltage and you go around a circuit and you come back to the same point, then the voltage at that point will be the same as when you started. So the total of the changes around the loop must be 0. Let's take a look at a simple circuit. Here you have a battery connected to a resistor, and I have grounded the bottom left-hand corner of the circuit. I put the grounding symbol there. That makes the potential at the bottom left-hand corner of the circuit equal to 0. That is the effect of grounding. connecting a grounding wire to the circuit makes that point equal to 0 volts. Now if I travel counterclockwise from that point, meaning I go across the battery, then I go up in potential. If it's a 1.5 volt battery, then as I go from the negative to the positive side of the battery, which I do if I move up, then my potential will increase by 1.5 volts. So the change in potential going from the bottom left-hand corner to the top left-hand corner is plus 1.5 volts. So the top left-hand corner of the circuit has a potential of 1.5 volts. Now I'll move from the top left-hand corner to the top right-hand corner. We're going across a conductor or a wire, so the potential doesn't change. So the top right-hand corner of the circuit also has a potential of 1.5 volts. As I move across the resistor, then I will experience a decrease in potential because I'm going in the direction that current will be flowing. So the potential will decrease across the battery. It will decrease by 1.5 volts so that now I'm at the bottom right-hand corner of the circuit where once again the potential is 0 volts, and then I'll traverse the conductor connecting the bottom right hand to the bottom left hand corners of the circuit, and I'm back to 0 volts. So the change in voltage as I made my trip was plus 1.5 volts to go across the battery, 0 volts across the conductor, negative 1.5 volts across the battery, 0 across the conductor, and I'm back to where I started, and those add up to 0. So the total change in voltage around any loop in the circuit is equal to 0. That is our first basic equation when working with electrical circuits. The total change in voltage is equal to 0 around any loop. The second of Kirchhoff's laws, we'll call it Kirchhoff's current law, is that wherever we have a junction, wherever we have a wire carrying a current, and the current can then split off, then the current into the junction has to equal the current out of the junction. So if I have a current I1 flowing into a wire, and then that wire splits off into two directions, where we have currents I2 and I3, then I1 must equal I2 plus I3. What that means is that whatever charge is carried by I1, it has to go either into I2 or I3. The charge cannot stay at the junction, so any current in has to equal the current out. So we are ready to work with electrical circuits. Our basic procedure, as always, is to draw a diagram, list all of your knowns and unknowns, and then start with your basic circuit equations, Kirchhoff's voltage law and Kirchhoff's current laws. You'll need as many equations as you have unknowns. A 12 ohm resistor is connected to a 16 volt battery. What is the current that flows through the resistor? Please draw a diagram of that. Use your Kirchhoff's voltage law as your basic equation, and please answer the question. Okay, let's draw our diagram. Here's our battery. The longer of the two parallel lines is the positive side. The other side is the negative side. It is a 16 volt battery. Okay, and we're going to connect it with wires to a resistor, and it is a 12 ohm resistor. And I'm going to assume that the current flows in this direction, from the positive side of the battery through the resistor to the negative side. And I'll call that I. And there's only one current because there's no junctions here. So whatever current flows out of the battery up to this point has to flow to here. All the same current has to flow here. All the same current has to flow here. And all the same current has to flow here. So whatever comes out of the battery has to flow all the way around. There's no junctions for it to split off. So there's only one current that we're concerned with. Okay. Our basic equation is delta V total is equal to 0. Let's start with this point right here. I'm going to start with that point. We're going to go across the battery. So the change in voltage across the battery as I go from negative to positive, that is a step up in voltage. So that would be plus 16 volts. This is a conductor, so no change in voltage. Now I'm going across a resistor and I'm going in the direction of the current. The current is flowing down across the resistor, so I'm going with the current. So when I go with the current, I'm going downhill. Just like if you go with the current in a river, you're going downhill. So as I go with the current in the circuit, I'm going down voltage. So that would be minus I times R. The change in potential across the resistor is I times R. And then I'm going across a conductor, so no change in voltage. I'm back to where I started. So that must equal 0. So I have 16 minus I times R, which is 12, is equal to 0. I only have one unknown, so I only need one equation. That's the only equation I need. So I have 16 is equal to I times 12. Or 16 divided by 12 is equal to I, or 16 divided by 12 is 1.33 is equal to I. And what are our units? Our basic metric units of current are the ampere. And we are indeed working with basic metric units. The volt is the basic metric unit of potential. The ohm is the basic metric unit of resistance, so the current will also be in basic metric units. So we will have 1.33 amperes is the current. Let's work another example. So here we have a circuit with 4 batteries in it and 1 resistor, and notice that one of the batteries is reversed. So you have to work with that. And the question is, suppose 4 batteries are connected in series as shown. If the current in the circuit is 0.4 amperes, what is the value of the resistor R? So please draw your diagram. List your knowns and unknowns. And once again, we know what equation we're going to be using. We're going to be using Kirchhoff's voltage law here because there's really only one unknown, which is R. So go ahead and do that and see if you can stay ahead of me. All right, let me redraw that circuit. We have a battery and a battery and a battery and a reversed battery. So positive, negative, positive, negative, positive, negative, and negative, positive. And that's connected to a resistor. And this is 3 volts, 3 volts, 2.5 volts, and 1.5 volts. We have a resistor of an unknown resistance. And I'm going to assume that the current flows like this, from this positive into this one. I is equal to 0.4 amperes. Now I could be wrong. What would happen if I'm wrong? I'll tell you what will happen. If I'm wrong, then we'll wind up getting a negative value for our resistance. And we know that that's not possible. Resistance is a positive quantity. It has to be positive. So I'm just making an assumption on the direction of the current. If I'm wrong, then we'll know because the resistance will be negative. Okay. What is our basic equation? Our basic equation is that the delta V total, or the total of all the changes in voltage as we go around the circuit, is equal to 0. So I'll start here. Start at this point, and I'll go clockwise around the circuit. Okay, so I'll start here. At this first battery, I'm going from positive to negative. I'm going positive to negative. That is a step down. So that would be minus 1.5 as I go across this one. But all 3 of these are then going to be steps up. So plus 2.5, plus 3, and plus 3. Okay, so that brings me over here. Now I'm going to go across the battery in the direction of the current. So I'm going down voltage, downhill, going with the current, going downhill or down voltage. So it'd be minus I times R. I'll write it as I, R. And that brings me back to where I started. That's equal to 0. Let's see, let's add all of this up. Minus 1.5 plus 2.5. That gives me a total of 1, and then I add 2 more 3s. That'll give me a total of 7. So 7 minus I, which is 0.4, times R is equal to 0. So once again, you see that we only have one unknown. So 7 is equal to 0.4 times R, or 7 divided by 0.4 is equal to R. Okay, 7 divided by 0.4. That's equal to 17.5 is equal to R. And 17.5 watts, well, we're dealing with basic metric units, volts and amperes. That means that this is 17.5 basic metric units of resistance, or 17.5 ohms. And that is the answer to the question that we were asked. What is the resistance of the resistor? Let's try another exercise. Here you have a rather odd looking circuit, but it's certainly possible to connect up resistors in that way. And the question is, each resistor has the same resistance, R is equal to 2.0 ohms. If a 32 volt battery is connected to the terminals A and B, what is the current in the resistor connecting points A and C? So go ahead and draw your diagram, list your knowns and unknowns, and you can actually solve this just with Kirchhoff's voltage equation. I'll give you that much of a hint. So see if you can stay ahead of me. Alrighty, let me draw my diagram. Okay, have all my resistors connected up. Looks like a wagon wheel. And then it said that we connected a 32 volt battery from point A to point B. So point A was in the middle and point B was right here. So I'm going to draw in a battery. And it doesn't actually tell us which way to connect the battery. So I'll draw it this way. Okay, I'll have the positive side over here and the negative side over here. There we go. And that is 32 volts. And each of these resistors is 2 ohms. 2, 2, 2, 2, 2, 2, and 2. And point C was right here. And point A was right here. And we were asked, what is the current in this resistor? So we're only being asked about this resistor. Okay, so there's a current I flowing through this resistor. And that's what we're looking for. We're looking for that current. Okay, what is going to happen in this circuit? We're going to have current flow out of the battery. Then it's going to reach this point, and once the current flows out of the battery, it's going to split off into different directions. Okay, and then once it gets here, it's going to split off again, and split off again, and the current's going to split off again. And the same thing, current's going to flow through all of these different wires. And these two currents are going to join up. Whatever current we get here and here are going to join up and flow across this 2 ohm resistor. But the important thing to realize is that we're not being asked about all these other currents. We're not being asked about the current here and here and here and here and here. The only current we're interested in is the one across the battery. So I can use my voltage equation, delta V total is equal to 0. And I'm going to start from the center. I'm going to go across the battery. So that's going to be a step up. And then I'm going to go around these wires. Now as I go around these wires, and it doesn't matter which way I go. I can either go this way or I can go this way. The important thing is that as I go along these wires, there's no change in voltage. So whether I go this way or this way, it doesn't matter. They're both going to add 0 to my equation. And then I'm going to close my loop by going across this resistor. And the voltage drop across this resistor is going to be I times 2 ohms. So that's the only current that enters into our voltage equation for that particular loop. And so we're only going to have one unknown in our equation. So once again, I'm going to start at the center, go across the battery, go around these wires, and then go across the resistor that we're interested in. So what does that make our equation? So from here, plus 32, then plus 0, plus 0, plus 0, plus 0, plus 0, and then I get here. Now I'm going downhill or down voltage by I times 2 ohms. So it'd be minus I times 2. And then I'm back where I started. So that equals 0. So you see, we have an equation with only one unknown in it. And that would be 32 is equal to 2 times I, or 32 divided by 2 is equal to I. Or 16 is equal to I, and it's 16 amperes, basic metric units of current. So that is the question that we were asked. What is the current through this resistor? And that's the answer. And in fact, the current through all of the resistors is the same, because I could do the same thing. I could come from here and go back across this resistor, closing that loop, and find that the current in this resistor is 16 amperes. I could go around this way, same thing. So the current through all of the resistors is going to be 16 amperes. And then by knowing that, I could actually figure out the current in all the rest of the wires using my current law. And we're going to next do an example where we do have to use the current law. Take a look at this circuit. The question is, if R is equal to 1 ohm and a 20 volt EMF is connected to the terminals A and B, as shown in the diagram, what is the current in the 2 ohm resistor? Now for this, you will have to use both your voltage law and your current law. So go ahead and draw your diagram, list your knowns and unknowns, and start to work on your equations, please. Okay, let's draw a diagram. Here's our battery, positive, negative, and it's 20 volts. And we have a resistor, and a resistor, and a resistor, and we have another resistor right here. And this is a 1 ohm resistor, a 1 ohm resistor, a 2 ohm resistor, and a 4 ohm resistor. Okay? And so we have a current flowing out of the battery. Let's call that I1. And the current flows from the positive side of the battery to this point here. At this point, it splits off, and let's call that I2 and I3. Okay, so I2 flows this way, goes across this 1 ohm resistor, and down across this 1 ohm resistor. So once I2 goes across this resistor, there's no place for it to split off. So whatever goes through this resistor also has to go through this resistor. So we still have I2 going in that direction. And I3 comes across this resistor, comes here. This is still I3. And then they join up again. So I2 and I3 join up again. And in fact, they give us I1 again. And so I1 flows across the 4 ohm resistor back here. And I1 flows into the battery. I1 flows out of the battery. There's no place else for the current to go. And there's 2 ways that we know that I2 and I3 come back together to give us I1. And that is that whatever there's only one current in this portion of the circuit, so whatever flows here has to flow here. So I1 and I1 here and here. Also, we have our Kirchhoff's current equation. I1 flows into this point and it branches off into I2 plus I3. So I1 must equal I2 plus I3. So I1 branches off, either goes this way or this way. I1 equals I2 and I3. And now when they come together, we have I2 plus I3 equal I1. So I2 and I3 come together and give us I1 again. So there's 2 ways that we know that. One is that this branch of the circuit has only one current in it, and the other is our equation. I1 equals I2 plus I3, or I2 plus I3 equals I1. Okay, so that's one equation with our three unknowns. We'll need two more equations. Our two equations are going to be our Kirchhoff's voltage equations, and we're going to do it two different ways, two different loops. I'm going to start at this point, and I'm going to make a loop like this through this triangle. And secondly, I'm going to make a loop around the square. That's two different loops. They're going to give me two different equations, and that will give me three equations for my three unknowns, I1, I2, and I3. Okay, delta V total is equal to 0. Let's go this way. From here, that's plus 20. Then I'm going down voltage or downhill across this resistor. I'm going with the current. So that would be minus 2I3. That's I times R. And then once again, minus 4I1. Minus 4I1. And I'm back to where I started. So that equals 0. And then I'll do it again. Delta V total is equal to 0 plus 20 minus 1I2 minus 1I2 minus 4I1, and I'm back to where I started, so that equals 0. Or let me simplify that a little bit. 20 minus 2I2 minus 4I1 is equal to 0. So now I have three equations. 1, 2, 3 equations in three unknowns. Here's how I'm going to solve them. I'm going to take this equation and I'm going to solve it for I2. I'm going to put that into this equation right here, and I'm going to eliminate I2. So I'm going to have an equation with just I1 and I3 in it. I'm going to take that and solve for I1, and then I'm going to take I1 and put it in here, and I'm going to have an equation with just I1 in it. So let's go ahead and do that. I1 is equal to I2 plus I3. I'll subtract I3 from both sides. So I1 minus I3 is equal to I2. So this is equal to I2. I1 minus I3 is the same as I2. So that gives me 20 minus 2 times I1 minus I3 is equal to minus 4I1 is equal to 0. So 20 minus 2I2, so 20 minus 2, I1 minus I3, minus 4I1 equals 0. Okay, 20 minus 2I1. And then I have minus 2 times minus I3. My two minus signs cancel out, so I have plus 2I3 minus 4I1 equals 0, which becomes 20 minus 2I1. 20, I have 2, minus 2 and minus 4, so that should be actually minus 6. 20 minus 6I1, that's a 6. 20 minus 6I1 plus I3 is equal to 0. I'm going to add 6I1 to both sides. So 20, I've got my 2 right here. 20 minus 6I1 plus 2I3. So 20 minus 2 and minus 4, 6I1 plus 2I3 equals 0. So 20 plus 2I3 equals 6I1, where I've added 6I1 to both sides, or 20 over 6 plus 2 over 6 I3 is equal to I1. So now this is equal to I1. So I can take this and put it into this equation, and I'll have an equation with just I3 in it, which I can solve for I3. Okay, so that would be 20 minus 2I3 minus 4 of 20 over 6 plus 2/6 I3 is equal to 0. Okay, so I have 20, and then I have minus 4 times 20 over 6. So 20 minus 4 times 20 is 80. 20 minus 80 over 6. That's my pure numbers. And then I have minus 2I3. And then, well, I'll go ahead and write that out. Minus 2I3. And then I have minus 4 times 2 over 6 I3. So that would be minus 8 over 6 I3 equals 0. Or, let me go ahead and figure out 20 minus 80 over 6. 20 minus 80 divided by 6 is 6.67 minus, and here I have 2 terms with I3 in it, so it'd be minus 2. And then since I've already pulled out my minus sign, that would be 2 plus 8 over 6 times I3 is equal to 0. And what's this term right here? So it'd be 6.67 minus 2 plus 8 divided by 6. That would be 3.33. I3 is equal to 0. And so I'll add 3.33 I3 to both sides, or 6.67 is equal to 3.33 I3, or 6.67 divided by 3.33 is equal to I3. And finally, 6.67 divided by 3.33 gives us 2.00 is equal to I3. And our units are going to be our basic metric units of current, or amperes. And that is our answer. The current I3, the current through the 2 ohm resistor, is 2 amperes. So we have to work with multiple equations and multiple unknowns. We'll do more of that next time. Until then, think physics.